Looking ahead, AI agents will continue to evolve. Advances in perception will allow agents to process multimodal inputs, integrating text, images, audio, and video. Advances in reasoning will allow agents to perform more complex tasks, combining statistical learning with symbolic reasoning. Advances in action will allow agents to control more sophisticated systems, from robots to networks. Advances in learning will allow agents to adapt continuously, updating models in real time. Advances in coordination will allow agents to interact in large multi-agent systems, shaping economies and societies. Advances in ethics will ensure agents are deployed responsibly, serving human needs while respecting values. The future of agents is expansive and transformative. When we move from individual agents to systems composed of many agents, the complexity increases dramatically. Multi-agent systems are environments where multiple agents interact, either cooperatively or competitively. These systems are important because most real-world environments involve multiple actors, whether they are humans, machines, or organizations. Understanding how agents interact is essential for deploying AI in complex domains. In cooperative settings, agents work together to achieve shared goals. For example, robots in a warehouse may coordinate to move packages efficiently. In competitive settings, agents pursue conflicting goals, such as trading agents in financial markets. Multi-agent systems require mechanisms for communication, negotiation, and coordination. They also raise questions of trust, fairness, and stability. Designing agents that can interact effectively with others is a major challenge in AI. Coordination among agents involves communication protocols, shared representations, and negotiation strategies. Agents must be able to exchange information, understand each other's intentions, and align their actions. Communication can be explicit, through messages, or implicit, through actions. Shared representations, such as common ontologies, allow agents to interpret information consistently. Negotiation strategies allow agents to resolve conflicts and allocate resources. Coordination also involves mechanisms for consensus, where agents agree on collective decisions. These mechanisms are essential for cooperative multi-agent systems. In competitive systems, agents must anticipate the actions of others and adapt their strategies. Game theory provides a framework for analyzing competitive interactions, modeling agents as players in strategic games. Concepts such as Nash equilibrium describe stable outcomes where no agent can improve its performance by changing its strategy unilaterally. Multi-agent reinforcement learning extends reinforcement learning to environments with multiple agents, allowing agents to learn strategies through interaction. Case studies illustrate the power of multi-agent systems. In warehouse robotics, multiple agents coordinate to move packages efficiently. Each robot must avoid collisions, optimize paths, and cooperate with others. Coordination mechanisms ensure that packages are delivered quickly and safely. In financial trading, multiple agents compete in markets, analyzing data, predicting trends, and executing trades. Agents must anticipate the actions of others and adapt their strategies. In clinical decision support, agents collaborate to analyze patient data, retrieve guidelines, and suggest treatments. Each agent may specialize in a different aspect, such as diagnostics, pharmacology, or patient history. Coordination ensures that recommendations are comprehensive and consistent. In adaptive tutoring, agents collaborate to provide personalized education. One agent may assess student knowledge, another may generate explanations, and another may monitor engagement. Coordination ensures that tutoring is effective and adaptive. In customer support ecosystems, multiple agents handle queries, retrieve information, and provide assistance. Coordination ensures that responses are consistent and efficient. Detailed architectures of agents involve pipelines, orchestration layers, and integration with large language models. An agent pipeline may involve perception modules that process inputs, reasoning modules that interpret information, action modules that produce outputs, and learning modules that update models. Orchestration layers manage the flow of information and can control the interaction among modules. Integration with large language models provides powerful reasoning capabilities. The agent structures the use of the model, defining goals, managing context, and integrating external tools. For example, a conversational agent may use a language model to generate responses, but also include modules for retrieving information, executing commands, and maintaining dialogue state. The agent orchestrates these components to provide coherent and useful behavior. This orchestration is what distinguishes agents from raw models. The model provides intelligence, but the agent provides purpose. Ethical and governance considerations are central to agent utilization. Agents may affect human lives, raising questions of safety, fairness, and accountability. In healthcare, agents must avoid harmful recommendations. In finance, agents must avoid manipulative behavior. In education, agents must avoid bias in tutoring. In customer support, agents must respect privacy. Designing ethical agents requires careful consideration of data, policies, and oversight. Transparency is important, allowing users to understand agent behavior. Accountability is essential, ensuring humans remain responsible. Governance frameworks are needed to regulate agent deployment. Without ethics, agents risk causing harm or losing trust. Bias is a major concern. Agents trained on biased data may produce biased outputs. Fairness metrics are needed to detect and mitigate bias. Privacy is another concern. Agents may process sensitive data, such as medical records or personal information. Secure methods are needed to protect privacy. Accountability requires mechanisms for tracing agent decisions and assigning responsibility. Governance involves regulations, standards, and oversight. These considerations are essential for responsible agent utilization. Personalization is another important aspect. Agents can be tailored to individual users, adapting to preferences, context, and history. Personalization enhances user experience, making agents more useful and engaging. For example, a tutoring agent can adapt explanations to a student's knowledge level. A productivity agent can adapt to a user's workflow. A healthcare agent can adapt to a patient's history. Personalization requires models that can incorporate user data and adapt behavior. However, personalization raises privacy concerns, since it involves sensitive data. Secure methods are needed to protect privacy while enabling personalization. Multimodal agents are another frontier. These agents can process and integrate multiple types of inputs, such as text, images, audio, and video. Multimodal perception allows agents to understand complex environments. Multimodal action allows agents to produce outputs in multiple modalities. For example, a multimodal agent can analyze medical images, interpret text records, and generate spoken explanations. This expands the capabilities of agents and makes them more versatile. Future paradigm shifts involve symbolic and statistical hybrids, adaptive ecosystems, and societal impact. Symbolic reasoning involves structured representations and logical inference. Statistical learning involves data-driven models and pattern recognition. Hybrid approaches combine both, allowing agents to reason with structured knowledge and learn from data. This combination provides powerful capabilities, enabling agents to handle complex tasks. Adaptive ecosystems involve large numbers of agents interacting in dynamic environments. These ecosystems can shape economies and societies, influencing markets, education, healthcare, and governance. Understanding and managing these ecosystems is a major challenge. Societal impact involves questions of employment, equity, and governance. Agents may transform industries, creating opportunities and challenges. Managing this impact requires foresight and responsibility. In conclusion, AI agents are systems that perceive, reason, and act in pursuit of goals. They provide structure around intelligence, making it purposeful and practical. Agents can be reactive, deliberative, or hybrid. They can be autonomous or semi-autonomous. They can integrate with external tools and systems. They can operate in domains such as healthcare, finance, education, robotics, customer support, and productivity. Multi-agent systems involve coordination, negotiation, and competition. Case studies illustrate their power in warehouse robotics, financial trading, clinical decision support, adaptive tutoring, and customer support ecosystems. Detailed architectures involve pipelines, orchestration layers, and integration with large language models. Ethical and governance considerations are essential, involving safety, fairness, privacy, accountability, and transparency. Personalization and multimodal capabilities expand agent usefulness. Future paradigm shifts involve symbolic and statistical hybrids, adaptive ecosystems, and societal impact. Understanding agents and their utilization is essential for mastering modern AI architecture, because agents are the practical embodiment of intelligence in action.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.